Hello everyone, I'm Greg Weaver. Welcome to the Audio Analyst. Today, I bring you the last video chronicling my remarkably informative and fascinating trip to the AGD factory in Aalborg, Denmark. In today's installment, we get to hear comments from Audio Group Denmark's chief designer and CTO, Michael Børresen. He is joined by the man who founded Gryphon Audio Designs in 1985 and who joined the AGD team in May of 2021, Flemming Rasmussen. Now, on a side note here, as Rasmussen is the 9th most popular surname in Denmark, he should not be confused with another famous Danish Flemming Rasmussen, the sound engineer, record producer, and owner and founder of the Sweet Silence Studios in Copenhagen, probably best known for his work with Ritchie Blackmore and Metallica in the 1980s. Regardless, here is their conversation. Let's listen. All right, everyone, here we are in Aalborg. We have Flemming Rasmussen with us, and we have Mr. Michael Børresen with us. And we're going to have some questions for these guys today about some of the new technology going on with Audio Group Denmark. First of all, gentlemen, welcome. Thanks for taking the time to join me today.
Okay, thank you.
I don't know where you'd like to start, but I would like to talk about the Class A technology you're working with. Is that something you're comfortable talking about?
Yeah, we have no problems talking and telling what it is
Good.
we're doing. So
lead on, sir.
Yeah, I think there are two elements to this. First of all, it was the first project Flemming and I did together. And when you see the casework and the design, I think Flemming's influence is quite obvious. It's bigger, it's bolder in design, it's more masculine in design.
They are very aesthetically appealing pieces. I think they look great. So, yeah.
I think they came out quite well.
They did, yes, no doubt.
But that was a very good process, and the way we work together is excellent. Flemming is very artistic and very visual in his way, and yet he's very traditional and simple in communication. So products typically start with ideas in a sketchbook, and I'm quite good with my CAD tools. That means that the sketchbook can quite easily and quite fast merge into something that has a visual. Yeah. So we can start talking details about on the visuals and then make adjustments, and in the end all that is transferred into a casework where all our ideas about resonance control, about ideas close to circuits are, and all our ideas about shielding are.
Yeah.
So I think that work has been good.
Yeah. Now you guys are you've kind of given up on aluminum, except in areas where it makes sense to use it. You're using a different case material.
Aluminium has that. Ask yourself how many musical instruments are made from aluminium, and you will find none.
Yeah.
Whereas other metals are actually used widely in guitars, in pianos, a lot of places you use metals.
Yes.
And all these metals in musical instruments are always selected because they have a pleasant tone. And when you do amplifiers, when you do speakers, every single material and the properties, the tone of that material matters. And you put something in that has an awful tone by itself, the product cannot sound good, because that tone will always be present in the presentation of what it does. And then you can talk about, it doesn't matter how good your amplifier is. If the tone of the chassis is bad, then you will still make a bad amplifier.
Yeah, but I was thinking about, while you were talking, that we were talking about different materials and why aluminum is so popular as it is. I think a lot of manufacturers, they probably won't admit it, have a tendency to idealize materials that are very nice to work with. So they're giving them qualities that they really don't have it, no. But it's nice.
But aluminium is pretty good for cooling. So when you make a big amplifier, you need cooling, so you need a lot of aluminium. So.
Well, I remember I had a friend who was making drivers, and he was using polypropylene drivers. And I asked him, why do you use that? No, it's great. It's the best there is, you know. And he was talking again and again and again about how fantastic that material was. But I also invested a lot of money in the machinery. There it was.
Snakker vi Per Skåning her?
Yeah.
Exactly. But that's
And
true.
he just would not leave it. He was hanging on to this material because
Of his investment.
of his investment.
Yeah, also
and
because it was so easy to work.
Yeah.
and it was predictable and everything. You know,
Yeah.
it was simple.
Yeah.
But
Well, I'm sure a lot of companies fall prey to that. It's a matter of cost. You know,
It
we
is.
own the equipment. We know it works. We're just going to keep going. And what you guys are doing in terms of pushing certain kinds of limits is not only admirable, it's incredible.
And when we talk about Class A amplifiers, I think that the world has seen many Class A amplifiers.
Sure, yeah.
And people think about Class A as a quality. And many are running under false pretense, really. Because most Class A amplifiers are really Class AB amplifiers.
Most, yeah.
And the reason is that they may burn quite a lot of energy to secure that they have the first 10 watts or 20 watts in Class A. But once you surpass that, they become
Class AB.
No, Class B.
Class B, okay.
Yeah, because then they go into pure switching.
Okay.
And for me, that was always, okay, is there a way that we can keep transistors from not switching? Can we always feed them a little more bias voltage than they actually need so that they will not
switch,
and go into Class A? So the bias spread needs to follow the signal, of course.
Okay.
It always does. The problem is that the bias spread, if this is a signal and this is a bias spread plus and minus, the bias spread always sort of diminishes.
Okay.
And it diminishes because the current is used for the base of the transistors, because the base of transistors are leaky. So current will run through the base and out through the emitter to the signal. So when you play an amplifier at a louder level, some of the current is actually coming from your bias stage.
Okay.
So the idea is, what if we really, really have a lot of current in the bias stage? Then we can, of course, keep them open longer. And then the next idea is, what if the traditional resistor here was exchanged by something else that was better at keeping this voltage?
Okay.
So what we do here is actually we take the diode from the output transistor and put it here. So we always have the same diode that's there. And then we just need to add a little bit extra. So we do that by a
That's
small
clever.
resistor.
That's interesting. Yeah.
So by doing that, even in a traditional circuit, we can actually keep the transistors on longer, even when the output device demands a lot of current. And if we then create a situation where most of the heat you're actually putting out is from the bias stage, we run 150 milliamps in the bias stage.
Okay.
And normally you run maybe 15 milliamps.
Yeah.
So we have 10 times as much current there. So we have a lot of current to draw from before the output transistors actually start switching.
Interesting.
And that way we can keep them open, even in 2 ohms load and full voltage swing, we can keep them open at all time. So the transistors stay on in Class A, output transistors stay on in Class A all the time, regardless how much current or how much power you actually want to pull out of it.
Yeah.
And for me, I don't understand why people for the building amplifiers keep on building the same amplifier they have been building for the last 30 years.
It's been a standard and it worked. People didn't seem to complain. But, you know, a lot of companies have stepped up and said that they use enough forward bias to run Class A to 12 or 15 watts, which is where most of your music is anyway. And then they switch to Class AB. But you're saying this new technology you're using lets you stay in pure Class A all the time.
Yes.
Now, the P880, I saw some of those that are almost done back there. I'm very anxious to get to hear those.
Yeah.
I'm hoping that we can work something out and I get a chance to hear those, and the C880 at some point. But what do you feel sonically the advantages you guys, just from that different circuit, have attained? Because the things that I hear with the new integrateds and unities, and there's a starkness to the backgrounds. There is a darkness from which everything emanates that is pretty unique in my experience.
I think that what we do with our noise cancellation creates that background. If we just get back to the amplifier and the topology, then when you have a Class A amplifier and you have built it is a folded cascade, and for those familiar with circuit would know that we make all the gain in one stage. And that means that we have only a 90-degree phase shift, which means it cannot catch itself.
Right.
So we will never have problems with oscillation. And that means that when we have the output, we don't need an output filter like normal.
You don't have to do the filtering.
Yeah, normal amplifiers has a few up to 100 microhenries
of filtering.
Yeah, we have 0.2 microhenries
Wow.
in the filtering. And it's just to avoid that when we put an electrostat on that has a phase shift by itself, because it's a capacitive load, that it goes to this 180, that then can cause oscillation. So we need to prevent very, very rare added speakers. On the Class D, you need an output filtering to eliminate noise.
Yeah.
So the advantage, I don't think there's any sonic advantage with Class A or Class D, really. But the output filtering is far less, and when we know how much inductance in cables...
You're dropping inductance,
So when you can drop inductance one place, it simply gives...
The benefits everywhere.
It benefits everywhere.
Yeah. So talk about the noise cancellation. Now you guys use something that you're calling Tesla filters, or Tesla coils.
Yeah, and the name is it should actually be an inverted Tesla. It should be an inverted Tesla coil. Yeah. And a Tesla coil is actually a transformer outside a transformer. That means that you can get humongous gain in voltage. Here we have a transformer inside a transformer, but opposite polarity. That means we can cancel. We can get from one voltage down to a much smaller voltage. Yeah. And when we can do that with high frequency noise spikes, we can transform those down to being smaller by using this. Then we are in a situation where we actually can cancel some of the high frequency noise that is present, whether it's on the main or it's something residual coming into cables.
Well, you do that in the cable designs. You do it in everything. I saw them in the M1s.
We do it everywhere.
Yeah.
And the reason we do it everywhere is that noise will creep in everywhere.
Sure.
When you have a piece of wire, it's
an antenna.
It's an antenna.
Yeah.
And that will absorb all the RFI that we have in the room. And the problem is that our world gets more and more polluted.
We've got three radios in our pockets. We've got...
And the thing is that this is something, when you do traditional audio, have this band, you cannot measure for this. It is something you can hear.
Yeah.
It is something, it's very, very audible, but it's not, it's very audible when you don't have the noise.
Well, and that's what I was getting at when I talked about the starkness. One of the things I think is crucial, especially in phono stages and things, is decreasing the background and self noise of the devices. And one of the things that struck me over the years since I first heard the Avik gear, which I think the first time I really got a chance to listen was probably Expona 2018-ish, I think, was there is this starkness, this blackness. It's quiet, okay, that allows everything to seem more, it pops more.
Yeah,
There's more.
The thing is that it's a skill to make quiet electronics.
Yeah.
It's a skill to find very low RBB transistors. It's a skill to make a good circuit board. It's a skill to make something that by component choice has very low noise. But apart from that, there's all the noise that we collect and put into the system. Sure. That when we connect to the internet, which is a floating thing, there's a world wide web of noise.
Yes.
How to get rid of that? How to get rid of and you see, I used to work in a company that does maritime communication, and this was a little bit the same, because you absorb from the atmosphere surrounding ships sending to you, and there's a noise gravel.
Yeah.
And how to look through the noise gravel? How to look through that? In the old days, when in World War II, they found out that radars were actually more efficient when they were
on the water than they were on land.
On boats, on cars, or whatever. when something is shaking. So a part of that, we have sort of two mechanisms. One is to shake the noise floor by injecting very, very low level noise.
Okay.
And the thing is that when you have something and it's a steady state, you cannot see what it is really, but if you move that a little bit, you can look through it. So our brain is very good at, our psychoacoustic capability is very good at picking up small traces of things that is hidden. If we just get a fragment and a fragment and a fragment, then we can put it together.
Interesting.
So I think that technology that was used as a maritime communication, this analog dither, very, very low level.
The dithering, yeah.
Is one way to create this background. And then all the Tesla coil cancellation that we have everywhere is another way of creating an absence of noise.
Well, it certainly seems to be very effective. All the demonstrations I've had here, and it shows that I've heard this stuff so far, one of the most apparent things about the electronics and the cables is how quiet everything emanates from. I mean, there's a definite degree of stillness from where all the sound emanates.
I think that another thing when you go on shows, the speakers are of course a centerpiece of that, and speakers needs to be quiet too.
Yeah.
So and again, there's a lot of these things that are measurable, and there's a lot of things that are not measurable. And this, how much noise does a speaker create by itself, by the motion, membranes flexing,
sure.
All these elements are also things that you could decipher and work with. If you have a membrane made from a softer material, this can be a Kevlar or carbon or whatever. When you have a softness to the membrane, you will always have tones where this membrane moves opposite of the signal. When you have a stiff cone, you will have certain resonances that you need to deal with. So it's always a compromise, and how to find the best compromises in that. There's also in speakers something people in general don't know about. That is, I don't even think speaker manufacturers are fully aware of how a speaker functions.
You're talking about a dynamic driver or the whole system?
Dynamic driver.
Yeah.
How a dynamic driver.
Well, some of the things that were made clear to me, I'd heard about, but were made clear to me here, so, like the printed zirconium baskets, the titanium voice coil formers. I was well aware of eddy currents and what they meant, but the demonstration of seeing the copper former versus the titanium former moving into the magnets and the eddy currents slowing the copper down. And you had mentioned that something that you guys take into account. I mean, you said aluminum. I'm sorry, not copper. Yeah. But you'd mentioned that people use aluminum because it's great at dissipating heat, more so than some other materials. But you counter that by being aware of these things, right? I mean,
I think most commercial driver manufacturers, they're very reluctant to use titanium because they would receive a shit a lot more drivers.
Higher failure rate.
Higher failure because they
don't dissipate the heat well enough.
No, a traditional magnet system has no ways of dissipating heat. So it's very nice to have an aluminium former. You can get the heat. You have a surface motion. You punch holes in them so you have
can breathe a little bit. Yeah.
Air moving in and out and around the voice coil former. That creates a lot better cooling environment for the voice coil. Here we put copper everywhere on the sides, so we take the heat off as radiation.
Okay.
But when we have a lot of copper around the voice coil, it becomes less hot. So we have a great heat sink built into the drivers, especially. But one way I talked about that people don't really know how a speaker driver works. But I think that's an essential question, because what are the dynamics? What happens when you put a current transient in? What happened to the flux in the magnet system? What actually creates the force that makes the membrane move? All these things are very vaguely described if you look at literature,
sure.
How a speaker works. It's just that you have a flux, and then for the ease of it, we take the flux from the magnet system as being a constant. But the voice coil, apart from carrying some current, is also a small electromagnet.
Sure.
And
Yeah.
the flux from that blends with the flux from the magnet system. And when you have iron inside, you can easily make the flux weaker by subtracting what the voice coil does.
Okay.
But you have a hard time pushing it up because it's very near saturation.
Okay.
So in any speaker system that uses iron, you have a built-in non-linearity from that. And that is, I believe, one of the main reasons why speakers make noise, because you hear that kind of iron distortion.
Okay.
But you will never measure it in a steady state, because it just means that the sine is a sine, but it's offset a little bit. But you will never measure that. So when you take something and you measure it, and a sine looks like a sine, it's very little distortion. But what happens under transient conditions is totally different.
Well, Lars showed us yesterday and today in the video tour we did the iron-free motors, and the use of silver and the opposing or the similar poles being forced together to increase the power of the magnets. You want to run through that a little bit and talk about that?
That was how to counter that iron thing, that type of iron distortion. Is there any way we can construct or design a magnet system where we don't have any iron? Is that possible? And it took a long time before that mechanism of, rather than conducting us to a certain flux, then pressing us, compression of flux together could form sufficient flux density to actually drive a speaker.
Well, it's pretty impressive to see. I mean, I've been around this industry a long time. I've not seen anyone doing what you guys are doing to build drivers. I mean, it's...
Well, they can't, because we have a patent on it. So
Well,
I think that nobody can go that route, or maybe they can find another way.
Yeah.
I don't know. But the route that we have gone is a patent of ours. So this is, but the magnitude of that is much greater than getting rid of the iron, because the magnitude of that, replacing the pole pieces with copper or silver, the magnitude of that is much greater than getting rid of this little element of iron distortion. It's because you actually put some tremendous lock on the flux of the system.
Okay.
Because any flux change from the voice coil is counteracted by eddy currents inside the pole piece and the two pole pieces that counteracts. And a direct measurement of that is how much inductance does the voice coil have. So by measuring inductance in the voice coil, you can see how high resistance your magnet system has to flux change. And with a low inductance in the driver, you have a much faster rise time and a much faster transient response. So inductance aids the resolution in the mid-range, low inductance. And I can say that if you take the free air inductance of the voice coil, it's about 0.5 millihenry. When you put it into the system, it's 0.08, and when you put it into the silver one, it's 0.06. So you see it's a great reduction of the induction of the voice coil.
Well, it seems a common thread is to reduce induction as much as you can throughout the system, and it seems to be pretty effective. I heard a lot of speakers yesterday. I heard a lot of demonstrations yesterday. And I got to tell you, I mean, this has been an eye-opening tour because, I've been doing this a long time, and and what I meant by not seeing anyone doing what you guys are doing, I wasn't just referring to the patents. I meant the attention to detail, the amount of time and energy and thought and effort that go into the designs and actual assembly of these products. We didn't talk about the 3D printed zirconium baskets. Those are amazing. What really struck me immediately was not that they were just a symmetrical design, but they almost looked organic. They had like a human kind of structure. They were narrow where they needed to be narrower. They were a little stronger and reinforced where they needed to have less flex and hold more weight. How did that come about?
That is artificial intelligence. So this is what happens when you ask yourself, what does this tiny bit of material do? Does that contribute to anything? If it doesn't, take it away. But the full idea of that is that the basket of a speaker is very, very much a part of the sonic signature of the driver.
It rings,
because when you have
movement.
Yeah, it's either in compression or in tension. So you have the spring of the basket is added to the music signal at all times.
Yeah.
The resonance frequencies, the way it stretches. So the sonic signature of the basket is very much a part of the performance of the driver. So when you have something tingy and ringy or aluminium, you get that signature. Yeah. And when you take it away, you don't realize how much that is until you take it away.
Well, it's pretty apparent when you hear it. I hope everybody gets a chance to go listen to some of these speakers, because I heard the M1s the first time I heard them, and I was like, it was funny. I walked into the room, Lars was playing Rammstein, full tilt. It was like walking into a rave. Okay, I mean, everybody was dancing, everybody was, and I'm looking around and I'm going, the SPL, and the thing that got me the most was the scale that this monitor was able to create, because the main reason I have large loudspeakers is to get around the limitation of scale that smaller speakers have. Now, you still do suffer some of that, but the M1 kicked ass. I was impressed with not only how tonally accurate it sounded, but its ability to scale very well.
I think one thing that people don't pay attention to or think about is that you have a big driver, you say, oh, this is very good in the bass. But what happens in the transient is that the membrane goes whoa. So actually the size of the driver in transients becomes much smaller than it is physically. And that happens to almost every single driver.
Yeah.
It's very easily detectable. It's easy. You can even, if you do laser,
you can measure it. Yeah,
you can see it. You can see this flexing.
Yeah.
And by having smaller drivers with very, very stiff cone, you don't get that. So essentially what you have is a speaker that has better grip on the low frequencies and more transient capability.
Better transient capability, definitely, yeah.
And again, if we can see fragments, we can understand the picture. That means that even if you miss some of the deepest octaves, if the overtones are correct, your mind will recreate it.
We were talking about that yesterday. I had a bunch of people who felt it was silly that a tweeter could go above 25,000 hertz. And I said, look, I'm not saying I can hear 25K, but there are fundamentals that create overtones. And when you subtract the overtones ability to be recreated, you affect the fundamental.
Yeah,
and
you have no good bass if you don't have a good tweeter.
Yeah.
The edges of everything come from the tweeter. But maybe you cannot hear 20 kilohertz. But if you play 20 kilohertz and 21 kilohertz at the same time, you will hear 1 kilohertz, because there will be a resonance or a Doppler pattern creating 1 kilohertz. So you have a different sound wave.
Yes. Yeah.
So it adds to the 1 kilohertz if you have 20 and 21 kilohertz on top of that. Then the 1 kilohertz will look different, and you can hear that. But the thing is that the audio universe is not so straightforward.
Yeah.
Like there are a lot of producers in our industry that relies too much on measurement and
Sure.
think measurements, clipper, whatever you have it is the king. But they sort of forget that in measurement there is a data. There is a data collection, there is a data management, and there is a data analysis. And that always comes down to the point that you have a mean of something. You have the middle. So when you look at the curve, and every single point of that is the sum of vectors. And when you have a transient response, we hear the vectors. We don't hear the sum.
Right.
So we listen in transients. We listen in and analyze. Our brain and our hearing, everything analyzes the frequency content of that transient. And that's what tells us whether something is really violent and far away or very subtle and nearby.
Yes, absolutely.
And we can detect that.
Yes.
That is a failure of measurements. It cannot detect that. So measurement can be you can find...
It's useful. It's very useful.
Yeah, when you do a speaker, you can find an error in the frequency content, but you can never find quality.
Yes.
The quality is more an understanding of what it is that creates quality, rather than you can never measure it. I mean, the best measuring drivers have membranes out of polypropylene because it's very good at absorbing. But polypropylene drivers sound like polypropylene.
Yeah, they do.
Yeah, and
they were really big in the late 70s and early 80s.
You don't want to be around that.
Yeah.
Because the quality is not there, but measurements are good.
Yeah.
So same goes with Kevlar membranes. You have this absorption of energy in a very unlinear fashion in Kevlar membranes. And when you build a speaker with a Kevlar membrane, it measures perfectly, but it's like putting a big carpet in front of your speaker. All the micro details, all the life and everything is sucked out of it.
Guys, thanks so much for this. Listen, is there anything you want to talk about that I haven't asked you?
Oh, I think if you go in depth, I think we could sit here for hours.
Gentlemen, thank you so much for this. I can't thank you enough. Michael, thanks for your time. I know you're a busy guy. Fleming, so good to see you, sir.
Good to see you.
Thanks, everyone.
Do my best to Stephen.
I will. I absolutely will, yeah. Guys, thanks so much. Everybody, thanks for watching. We'll talk again. My sincere thanks to Michael and Fleming for taking the time out of their full development and production schedules to share this time and discussion with us. I hope you've enjoyed this multi-part, all-access glimpse into Audio Group Denmark's intriguing and remarkable facility and all the background on the wide range of technologies they implement across all three of their product lines. Again, I want to express my sincerest thanks to Lars Christensen and to the entire AGD team for their generosity, both in hosting my visit and allowing me to relate their remarkable story. I'm looking forward to sharing more detail with you on some of these products as I get my hands on a number of them, including Børresen speakers, Avic electronics, and Anzus cables and accessories. Now, before I close today, I have to mention an upcoming milestone. This coming Wednesday, March 1st, will mark the 50th anniversary of the release of the LP that still holds the record, and by a monstrous margin, for consistently remaining on the Billboard Top 200 record charts for an astonishing 917 weeks. That's over 17 and a half years. Of course, I'm referring to Pink Floyd's 1973 prog rock masterpiece, The Dark Side of the Moon. This kind of staying power was so unheard of that when the record finally fell off the charts in 1988, even the Wall Street Journal covered its significance. And when I reminded Gail Sanders of this upcoming milestone during an unrelated phone conversation this past Thursday, he was as astonished as I was, sharing equally in my disbelief that it had been 50 years since its release. If you haven't listened to it in a while, you might make some time Wednesday to rediscover an album that still holds the #1 spot on Rolling Stone magazine's 50 best progressive rock albums of all time. I'll be playing this copy. I hope you'll join me Wednesday. As always, thanks for taking the time to drop by. Further information on supporting the channel may be found in today's description section or at my website, theaudioanalyst.com. Please stay safe and keep the music playing. Till next time, Skål.